This is a quick lesson about how to make alkenes, how to make double bonds from alkanes from an indirect route. In the past, what we've been doing is being able to grab a bromine or a halogen and remove that in different manners and then attach or substitute or eliminate through those means. But what if we have a different kind of situation? So this is going to be an indirect route to an alkene from an alkane. So we're going to look at a couple of different things here. So we have two reactions that could occur if you have just a normal alkane. So you have no functional group at the moment. Meaning an alcohol, a halogen, we have nothing to grab onto. So we would have to do a little extra work. So we could add a bromine. So through halogenation, which we've done with a radical, and then once we have that bromine, then we can do some elimination. So the key point to that is that we need to introduce some sort of functionality. By introducing that, now we have the ability to remove it and manipulate and add our double bond how we would like to. So if we look down here, we have a couple different options, and it's already all there for us. But what if we started on the left side? So imagine you can't see the right side of this yet. This is non-functional. Notice what we're doing. We are adding a halogen, and either we're adding a bulky base or adding a normal base. So in the middle, our intermediate, right, we're going to have our bromination. So there's our bromine. And then we have two results, and these should not be surprises. These are my eliminations, as we said above. So we have halogenation first. Right, this is a disubbed alkene, and with a normal base, we have a trisub, so that's Zaitsev, right? We have Zaitsev. So that's still going to all follow suit. So let's try to do a little predicting here. So we're going to provide a recipe. So I'm going to go from my alkane to my alkene. So what would be needed first? Well, first, I would need to introduce a little bit of energy and a bromine diatomic. So what's that going to make? Let's try that again. It's going to make a alkane with a bromine attached. Now you might ask yourself, well, why right there? Well, if you take a look, my double bond is on that location. So I would need to have it on at least one of those carbons, correct? Well, we don't want to have it on a primary because a primary is not good for an E2 reaction, right? A primary only works for SN2, so that would stunt and stop this reaction immediately. So I want this on a secondary carbon, minimum. All right, then let's take a look at this. What do I see here? What type of elimination was this? Well, this is Hofmann. And what does Hofmann deal with? Hofmann deals with a bulky base. So you can put any base you'd like. Let's just do an easy one. So let's just do NET3. And there I am. That's how I would get that first one done. So like before, I need to create a elimination site. So I'm going to add my bromine with some energy. Where would I want to put my bromine? I want to put it at the most substituted area possible. So that's going to be right there, the most highest amount of carbons connected. So that's a tertiary right there. Then, what am I talking about here? Well, if I take a look at that carbon substitution, that looks like Zaitsev. So what I'm going to need is I need a normal. And this is material that we have covered as we've been introducing our normal versus our bulky nucleophiles. So you need anything at all. It could be NaOH. It could be OCH3. Basically, what you need is an anion, right? As long as it's an anionic normal base, you're good to go. So that is when we have just a pure alkane going to an alkene. Different scenario. What if we have an alkene as our desired reaction product and we start with an alcohol? All right, this is going to be a little different. It's going to be a little trickier. So the key to this is my alcohol, right? Well, if I take water, H, I'm going to produce water, HOH. So how that's going to occur is I'm going to need an acid of some sort. The acid is going to allow that OH and that H to leave. By losing both of those, I'm going to expose those electrons, which will eventually collapse and create that double bond that I'm looking at right there. Okay, so let's take a look at what we're looking for in these reactions here. So we have 3 of these right now, and they all look very similar in the beginning because of the reaction arrow, but there's some unique items on each of these. So if you look at this first one, we're going to try, again, to eliminate that alcohol. So I could pick either way. I could have my double bond going to the right or going to the left. Well, it appears that it went to the left. So it is very important that you start realizing with alcohols, we also want Zaitsev. I like to think of it as the acids look more normal. They're not as bulky. So if they're not bulky, they can get in there. And if we can get into that compound, that means then we're going to have the most substituted double bond possible. So we're going to have a major Zaitsev. If you did, it says plus some isomers. Well, that would be the minor. And the minor for that would be linked off of the same carbon. We need to be on that carbon right there, right? So we would have that as my other option, and that would be my minor. But my major is a Zaitsev. All right, let's take a look at the second one. This is an interesting problem because if you look at this, again, I had my OH on the top right here, so it's going to move down. Let's take a look at the minor. So there's my CH3. The minor would try to be less substituted, so that would go up there. Well, let's take a look at this for a moment. If you would look at that H, if I'm exposing and removing, I'm removing this OH right here, that is a cis H. You would think that that's not okay. But in these cases, because of how the geometry is going to be afterwards, it's okay. So there are no requirements for a trans hydrogen. That's okay. And I know that's going to be confusing as we go, but that's part of working on these problems. We'll figure that out as we go. So we want Zaitsev. We have no requirements for trans H. And then the final one, if you just look at it again, definitely again, we have Zaitsev. Continue to write that to try to hammer that home. But my alternative minor product, most likely, would be something like that. Right, the less substituted C. So let's look at the mechanism, which can be a little confusing. We'll get some practice on the next sheet. There are 3 steps, and I'll highlight them right away. It's right here. Protonation, elimination, and deprotonation. If you think of protonation, protonation is adding an H. You're really just adding an H. And I'm going to actually write this beforehand. So we're going to add an H. Let's write it a different way. Deprotonation means that you're subtracting an H. So you're going to have a loss of an H. And then we'll eliminate something, which we'll talk about in a second. So let's look up above. Again, I have my protonation, I have my elimination, and I have my deprotonation. Let's do one step at a time here. So the goal is to have that OH leave. Don't draw this, but a lot of us in the beginning, when we have bromine, you want bromine to leave. Here's the problem. OH minus is a bad leaving group. It's a very bad leaving group. It's difficult to leave. It's not going to be able to remove itself very easily. So that's what makes it a really bad leaving group. You want a group that can be removed quite easily. So that is not going to happen. So what we need to do is we need to So we are going to take these electrons and we're going to give them to one of those H's on the acid. What does an acid do? If you can remember back way in the beginning of this year, is that acids, this will help you a lot. Acids donate H's. So if you can think about that when you're looking at this problem, like, okay, so there's my acid. It's going to give away an H. I know it looks like it's the opposite with the mechanism, but those electrons are actually creating a bond to that H. Okay, so now I have 2 things here. Notice that this is now my, and I'm going to kind of, this is not the mechanism. Anything that's green is not the mechanism, but that's what it becomes. I get HSO4 minus. And then notice that my water is now protonated. My water is now protonated. It has a positive OH2. So to remove that, if I give it some electrons from the bond, it becomes water. Again, green is not part of the mechanism. So this becomes neutral water. And neutral water is a great leaving group. And there it is. That negative is not there. Okay, so now we have eliminated water. I'm going to write that right here. Elimination, you need to get rid of water. That's your elimination. So let's quickly update what we have here. Is that basically here, you're going to go from OH to OH2 plus. You're going to eliminate water, and then you're going to lose an H. So now what we need to do is lose our H. To lose the H, it will create that double bond. So right now I have a carbocation, and you can see it right in front of deprotonation right there. And simply, I need to take, it could be a lot of things, you guys. It could just be H plus sitting out here. But it's going to attack that water, attack that carbocation, which closes itself off, and that's my elimination right there. And now I have the double bond, and it kind of repeats the cycle. I've created an acid again, then now it can start all over and react with the next compound and the next and the next. Because we're in an acidic environment, it's going to continually be able to do that. But you can just think about this as instead of HSO4, you could, oops, you could think about this right now is that I just have an H plus floating around because that's what just occurred. That's what an acid really is all about, and that H plus can help with that deprotonation. That's the goal. I'm trying to release that H. So a couple things under here. And there's a lot written here, but you want to understand reactivity. It's still the location of my alcohol is similar to the location of a bromine. So I want reactivity. Okay, what's bad? Primaries, vinyls, things like that. Okay, allylics, tertiaries, secondaries are great. That's great. Okay. We will talk about this later when we start trying to manipulate and maybe make an alcohol from an alkene, is that you need to just understand that this reaction is reversible. If you look up top, that double line up here, that means it's reversible. But we're just talking about the forward reaction right now. So let's move back down. So that being said, let's do some predictions so we can kind of see how this is put into action. Okay, if you just have to predict and you don't need to do any kinds of mechanisms, these are not too difficult. Just a word of advice, don't make these too large. We're going to do a couple mechanisms on these. Of these 5 problems, we're going to do 2 of them as mechanisms. So I would just draw the base again on here. I know that the OH is going to leave. And my goal, you guys, is Zaitsev. So I have 2 choices. I can either go right there or I can go right there. Zaitsev would say I'm going to go where the more substituted carbons are. So that would be my final product. The second one, same concept, you guys. I can go there or I can go there. Your goal is Zaitsev. So I'm going to give you a second to think about that, where that would go. Hope you're thinking that. That is Zaitsev. Take a look at that one. Again, I have yet another possibility of either that location or this location. I'm going to pick that one. That is a tri-subbed double bond. All right. A little funkier, number 4. So we have a couple scenarios here. I just need you to understand this. And this first one, Z is OH. So I'm going to write on mine. You may not want to write on yours right here, but I'm going to pretend that that's OH. Okay. What if it's going on with an OH versus a bromine? I want you to see the difference. OH is new. Bromine's actually an old reaction that we've had in the past. So what is occurring here? Let me just draw my base there. So I have 2 choices. I can either go here or here. Correct? With alcohols, you guys, it doesn't matter. It doesn't matter if it's a cis H. So what you got to realize is that there's a CH3 right here. If I put the double bond this way, I am more substituted. And that would be Zaitsev versus going to the left because there is not a CH. So that's actually the one that I'll want. And then I put the deuterium still there. So that would be my most favored reaction. Let's take a look at something that we've done in the past. So if this is not OH anymore, but now it's Br. Well, now what we need to do? Well, okay, let's take a look at this. First off, this is what we call a normal nucleophile, right? Not bulky. So if it's not bulky, then I have the ability to do an SN2 and then an elimination. So let's first do my SN2. So this is just a normal reaction that we've done in the past. So I'm going to take that Br and I'm going to have inversion because that's what occurs. So that's going to be inverted. Everything else maintains the same stereochemistry. I'm not going to include the H's just to not clutter it up. That's my SN2. Okay, let's talk about the E2 for a moment. So I'd slow down in what you're going to be writing here because we want to make sure that we're understanding this. Again, what we're either going to have, you guys, is either that as a double bond or that one as a double bond. And we have to determine which one would be right. Now, if you're like, well, it's going to be just like it is on the top. Here's the problem. With something like this and a bromine, we have to have, you must have a trans H for Zaitsev to occur. That would be the best with the most substituted carbons as well. The problem is here is that you have a cis H. This is a cis H with this bromine. So it has to attack that other H. It can't go with the most substituted. So it's have to go on the other side. So it's going to look like this. And this is a little confusing, so you're going to have to really kind of understand the reasoning behind this. Is that the right side is going to be unaffected, and it has to go on this side. So it's Hoffman. Sorry, I missed an N. And it's forced. And it's forced because in Zaitsev, there was no trans H. The formation, if it would have achieved Zaitsev formation, you would have needed a trans H. So that was not going to happen. So in this case, unfortunately, that is the only E2 that's going to occur. We can't go the other direction. Okay, let's talk about a couple mechanisms. I think that's going to be really important for us. So I'll do this in red. I'll try to keep this as clear as I can. It's going to get a little tricky here. I'm going to make a line right here just so we can kind of try to keep this as clean as possible. So if I start with my structure right here again, let's do number 2 first. I think this is a really good one. And let's include everything we possibly have here. So I'm going to put all my H's because some of these H's have to collapse and leave and create double bonds. So I think it would be really important to show that. Oh, I'm sorry. That's a methyl. That looks better. All right. So the first step is deprotonation. It's very important. We got to get that. We got to activate that OH. Think of it that way. We got to activate that OH. You can choose literally any acid you want, but in this case, I'm actually going to be using the one that's provided there. A lot of times you're going to see this as heat as well. So if you ever see that, that works out okay. So I need to activate that. I need to go get one of those H's. I need to go get an H. So I'm going to go get that H. Remember, dots or bonds, 2 atoms. We always are doing that with our mechanism. So this is my first step. All right. So then what's made? Well, let's take a look. That area is unaffected. And now what I have is a little bit of a juiced up hydroxide. Right? I have an extra H. That extra H causes it to be positive. All right? So let's think about what needs to be done to that. Right? If I'm going to, that's going to be the site where I'm going to probably be reacting, right? Well, I'm going to try to get rid of it. Okay, this is the most important step of the entire mechanism. This is my elimination, right? This is the slow step, really, creating the carbocation. This is the one that causes the rate of a reaction to be determined. So I'm going to cause this bond to break and give the electrons to that positive. Again, electrons will go to where the positives are. Opposites attract. Opposites attract. So because of that right now, then, if that electron leaves, I have an H right here. Now, I'm trying to make a carbocation eventually. So that carbon is a little juiced up with positive. And then what do I have sitting over here? I have my now neutral water. You don't have to draw it like that. You could write H2O, but I'm just trying to show you kind of how that would look like. And now, ultimately, you guys, that's my second step. if I want to finish this off, how do I get that double bond to collapse? Well, in theory, if you take a look at this, I need to get rid of that bottom H. Well, how am I going to get rid of that bottom H? Through multiple means. You could think of it as just an H plus sitting around. You could have this H plus. You could have HSO4 minus. There's a lot of ways you can think of it. I like the HSO4 minus personally. You're going to take that electron and you're going to attack that atom, and then that bond is going to collapse. Those electrons are going to be given to the positive. Again, if you ever have a positive cation, at some point you need to think about a bond or electrons going towards it, and then that creates my double bond. So that stems from an alcohol, and then it's making a double bond. Okay? And that's my third step. All right, let's do this a little faster, and you can replay this as many times as you need. So let's take a look at this. Let's take a look at this top one. So if I just start way to the left, and I just make my alcohol, butanol. And what I want to do, I'm going to do these in a different color. You got to realize that there's an H in here, and then I realize that the double bond's going to be between those two carbons. So let's put the hydrogens on there. So I'm going to react it with H2SO4. And again, what I'm going to do is I'm going to take those electrons and try to steal one of those H's. Remember, an acid tries to give away an H. So now you can kind of write it like that. It's an H, it's an OH plus 2. Oops. And that's a carbocation. And then what's going to happen? Well, you want to get rid of that now. Now we can release that water. So release that water. Those electrons are going to go to that O. Right? And by doing that, now I'm going to have a charged up carbon. So I have these two H's sitting here. Right? Technically, I got my H2O now. Right? And then to finish it off, I'm going to make my double bond. And I can do that in a lot of ways. I would like to write it like this, though, if I can possibly do that. And how's that going to go? Well, it's going to take one of those H's. Let's just pick that one. And then that's going to go to that bond. You got to keep remembering, you guys, if you're going to make a double bond, it's got to come from electrons, probably from something that is leaving that that compound. So that would work quite nicely. So please take these ideas, rewind them if you need to, and apply it to your worksheet for today.